Colleague. In 2020, she co-chaired FABRICATE together with Jane Burry, who, by the way, also is here. Jenny is a core member of our community and really a stellar point in keeping our research discourse astute, precise, and critical. Jenny is Arthur L. and Isabel B. Weizenberger Professor of Architecture at the Department of Architecture in Cornell University, where she runs the Sabin Design Lab, which is in deep connection with her Jenny Sabin studio. Her work examines how design and emerging technologies can drive new directions for the 21st century architectural practice. She investigates the intersections of architecture and science and applies insights and theories from biology and mathematics to the design of material structures, creating a new ideation of how computational design, data visualization, and digital fabrication can be brought together. She's a key voice in our architectural research community. She has won multiple esteemed grants from the U.S. National Science Foundation, the National Academy of Engineering, and the Granger Foundation. She is now Vice President, former President of the Arcadia Association. She's the recipient of very important fellowships, including the Pew Arts Fellowship, the Knights Fellowship, and the Architectural League Prize. She has exhibited in leading venues, and her work is included in collections of the Cooper Hewitt, the Smithsonian Design Museum, the Centre Pompidou, and the Frac Center. And exciting for us here in the local audience is that Jenny has been invited to do a new show at our esteemed Louisiana Museum an hour out of town. So we know that she'll be in and out of house, and we're looking very much forward to that. So thank you so much, Jenny, for chairing this session.
Thank you, Meta, for that kind introduction. It's a pleasure to be here. How great is it to be back in person? Just amazing. Okay, so it's really a pleasure to chair this panel, which is titled Integrate Systems and Context, with my esteemed presenters and dear colleagues. House of Cores by Leslie Locke, Sasa Zivkovic, and Fabian Meyer-Brötz explores what they call deep collaboration through the first two-story 3D printed home in the US to unearth new possibilities for resource-efficient construction. Locke and Zivkovic view collaborations with industry as a necessity to scale that also present opportunities for sustainable uses of concrete with less cement. Chadha and Lauren Vasey will present impact printed structures, design systems, and construction strategies. Their innovative robotic earth building technique, titled impact printing, mitigates the typical formwork dependent and labor-intensive processes in earth construction to take advantage of the, quote, high thermal inertia, moisture regulation, fire resistance, and acoustic insulation that earth construction provides and always has. A fundamental goal of their project is to bring rammed earth construction processes to market, which will require automating the entire pipeline. Julia Fleckenstein and Bruno Knychalla present Breuer XAM, functional hybridization in concrete building elements through additive manufacturing. Breuer XAM is inspired by the pioneering methods developed by architect Marcel Breuer in the 1960s to address the, quote, complexities of multi-layered building systems. Through a modular precast facade panel that integrated building services, installation, and passive solar protection. Breuer XAM also features functional integration and non-standard differentiation through prefabricated single material units that look towards the future life of a building, such as deinstallation of the units and circular material reuse. Breuer XAM is a daughter company of an industrial 3D printing company with a strong desire to scale and couple with the construction industry. KNITNERVI, Lightness and Tailored Materiality for Flexible Concrete Construction by Mariana Popescu, presents a computational workflow for the design, fabrication, and installation of a flexible formwork system. The project uniquely combines design, structural engineering, and fabrication, importantly breaking down silos, to innovate not only new strategies for knitted flexible formwork, but also incredibly lightweight, efficient, and self-supporting systems that can pack flat for transport and be deployed without the use of heavy machinery such as cranes. In reading the selected project papers in this section, and through our pre-session discussion last week with the panelists, a few common themes and questions emerge. What is the added value of customization? How does one negotiate customization versus standardization in stitching together architecture, engineering, and construction, while also importantly identifying resource efficiencies? Hurdles identified by the panelists include total resistance from the construction industry, which points to issues of labor and economics. As Bruno stated, radical innovation in construction can cut a lot of people in the middle out, and thus risk eliminating jobs. Additionally, vertical integration in construction is fully integrated and streamlined from developer to contractor. But this promise can only be solved with adequate funding. As Lauren points out on the topic of collaboration, quote, besides silos, there is structural liability, calling for a radical new approach to typologies of structure and perhaps a renaissance in engineering, end quote. On the viability of on-site construction versus prefab processes, Bruno and Sasa argue that ultimately the market will determine which construction process. And therefore, economies of scale will still apply, and we are still interfacing with conventional construction processes. Clearly, to address some of these challenges and make change, we need to change the structure of academia, to break down silos, and some panelists argue that fabrication needs a disciplinary home. The authors in this session bridge the gaps between architecture, engineering, and construction through robust collaborations with industry. But if they are, quote, too technical for architects and too artistic for engineers, end quote, perhaps a new academic silo focused on fabrication is exactly the opposite of what we need to close these gaps. As Violet Whitney writes, if the Renaissance called for a science of the making of buildings and ultimately pushed architects, engineers, and those making buildings to split and therefore develop separate and strategic methodologies, why did this split happen? Which was further substantiated in the 18th century with the establishment of separate schools of engineering. Perhaps the divorce between architecture, engineering, and construction, one shifting towards qualitative aspects of architecture, including aesthetics, and other towards quantitative structural analysis and computation, is due for a new model. Maybe the science of building never called for a split. And here we are, as articulated in each of these incredible projects and was brought up in the previous panel, innovating in a new paradigm and constructing in an old one, which fundamentally negates resourceful futures. The type of integration and collaboration between research and practice across disciplines is not only needed, but necessary to address the complex environmental, social, and cultural problems and injustices of our time. For example, can distributed design networks and microfactories contribute to next generation methods of low cost, efficient, sustainable, and innovative fabrication and construction strategies? As seen through the integrated work in this session, indeed 3D printing, advanced manufacturing, and robotics are transforming how we make, construct, design, do business, and engage with our communities. I see correspondences between these integrated advancements in fabrication and a design philosophy rooted in the science of building, where architecture, engineering, construction, and the sciences come together. At a time of ecological catastrophe and socio-political and cultural challenges caused by our deeply entrenched misconceptions of human dominance over nature and our planet, integration across systems, context, and disciplines has the potential to open new models for teaching, research, and practice to address these urgent questions and crises. A cross-disciplinary collaborative practice where playfulness, impactful creativity, generosity, and connectivity thrive opens new possibilities. I partially agree with Lauren. Engineering does need a renaissance, but not a new one, but a simple return to what has always been latent and should have never been split into disciplinary silos, a shared vision and profession for the science, art, and making of architecture. The projects in this session offer insights and next steps. So with that, I would like to invite, Lauren Vasey and Chadha, who will be presenting design systems and construction strategies for impact printed structures.
Hello, everyone. Firstly, thanks a lot for this opportunity to let us present our research that we have been developing for the past few years. My name is Kunaljit Chadha. I'm a PhD at Grammaticula Research, situated at ETH Zurich, and I'm with
Dr. Lauren Vasey, and I'm a postdoctoral researcher at ETH Zurich. And we are going to present design systems and construction strategies. But before we jump into the context of the paper, I want to give you a little bit of insight into the underlying research project. So we are all here today because of the huge problems that the construction sector is facing. We are generating almost 40% of the global greenhouse gas emissions, 20% from new construction alone. And we're producing hundreds of billions of tons of waste, 35% which is sent to landfill, because our methods are non-circular. We're also stagnating in productivity, and we're facing a global labor shortage. Excavated material and earth-based material is an excellent candidate for a circular building material. However, there are huge barriers to industrializing earth-based materials. We have on the one hand side rammed earth, which is a traditional construction method which has been industrialized by companies such as Lenton Erde and Erne. However, there are still high relative costs relative to concrete. There's many manual steps and low levels of customizability. On the other hand, we have emerging additive manufacturing possibilities. However, when we're using pumping-based solutions and we're requiring a lot of additives that enable us to quickly take a liquid material and then transition it to a very solid material, we're actually compromising many of the circularity benefits and also oftentimes adding to the embodied CO2. So impact printing is a research project that was initiated 4 years ago by 3 different chairs, Grammaticula Research, the Robotic Systems Lab, and the Chair for Sustainable Construction. We originally were funded by the ETH grants, but we've also now become an NCCR affiliated project. And we've also received funding from different initiatives and also the SNSF. So the project was really based on this aim of taking earth-based construction and industrializing it, pushing it to full scale, and pushing it on site. So the goal is to use an autonomous construction machine as one of the ultimate platforms to enable a breakthrough at scale, but also to push the construction speed and the throughput so that we can really facilitate a low cost that will enable us to enter the market. So the benchmarks for industrialized construction include: we must consider costs, we have to consider an efficient build rate, we have to consider the parallelization of tasks, we need a high level of automation, especially in Western contexts where the cost of labor is expensive, no formwork dependency, and we need to really think about the additives and whether they compromise the embodied CO2 and the circularity. So we wrote this grant 3 or 4 years ago, so it's super exciting to see it come to fruition now. We were very lucky to hire Kunal from IAC to gain a lot of knowledge from 8 years of earth-based building methods. And Ananya is also here in the audience, so if you see him, feel free to ask some questions. But we work also with the Chair for Sustainable Construction. They help us with the material development, and also the Robotic Systems Lab on autonomous robotic systems. WASP has been an industry collaborator on extrusion systems, and with a local construction partner, we're working on a circular mix design and supply chain. So this is maybe not as loud as it could be, but this is our new additive manufacturing method. So we have developed over the last 3 years a completely custom machine. It's obviously very high payload, but basically it takes very high dense material, it portions it, and then it shoots it with a very high velocity. So the velocity is 10 meters per second. And by shooting it at a very high velocity and controlling the velocity, we can actually enable bonding between the parts, even when the part starts with a very, very high yield stress beyond what is pumpable. And because we're starting with the material in a higher yield stress, and we're building with it, actually what's very exciting is that we have a very high stable height buildup, and we don't need to stop for construction pauses to wait for green strength development. So we've been able to achieve a very thin structure, so 0.1 meters in thickness, that are 1.85 meters, that are only built in a few-hour construction session. And second, for the goal, we really want to develop our whole fabrication process for transitioning it from an off-site fabrication environment, which is very structured, which enables prefabrication, and transition the whole hardware, control, and software to an on-site construction platform. So we're developing everything so that we can ultimately transition it to an on-site autonomous excavator. So now I'm going to pass it over to Kunal, who's going to give you some insight into the paper and the off-site prefabrication.
Thank you, Lauren. So to assess this factory on the fly setup that we have in the prefab off-site scenario, the software or the design and the fabrication workflow was introduced in a project, in a studio project at MAS at ETH. There's a small link that you could maybe scan and get more information about. And the focus topic of this studio project was to make embedded timber frames to create architectural openings in impact-printed structures. As a given, the students were introduced to a set of hardware and software tools developed by the research team. They were introduced to our experimental setup on the prefab configuration, where it has the assembly that you just saw in the video before. It comprises of a hopper-based extruder and has a portioning system and then a shooting mechanism which shoots the parts at a very high velocity to have a compaction on impact and hence impact printing. So what we see here is that this end effector then is mounted on a bridge-like structure, which is then manipulated in Cartesian space, synchronously programmed for 2 robotic platforms in a gantry system. The material mix which was used for the studio was a low impact mix developed by Chair of Sustainable Construction, which comprised mainly 75% of construction byproduct material donated by Eberhard, which is a local construction company in Switzerland. And it's topped up with earth-based materials such as sand aggregates to have the compressive to take the compressive loads, and also clay to enhance the adhesive properties for the process, and minimal amounts of stabilizer. To create a robust pipeline from design to fabrication, the students were also introduced to an object-oriented design library, which discretized intended geometries into impact printable trajectories for the operation. And as an addition, the control environment also included, you can see here on the bottom, an insight on the production information. So it gives you a quantitative estimate of materials to be mixed and while construction and to plan the logistics around the fabrication process. So one of the main goals, or one of the main challenges for the computation methods, is to achieve a consistent overlap between the parts, to have an even volumetric buildup, since it's a remote deposition process. Here, maybe it's a bit more evident, but this is a picture showing a part in 3 phases. The one on the left you see is a part when it's extruded, the one in the middle when it's compressed for the shooting process, and the one on the right is when it's shot, which leaves an elliptical footprint, which makes it difficult to achieve this consistent overlap over curvilinear trajectories. So this was handled computationally with an iterative method. So algorithms were developed to space them evenly and then try to find a consistent overlap area and then divide it for the whole structure. So for a single curve, there are many ways you could do it, but this has to be computationally handled. For larger structures with thousands of parts. So this was tested in this tapered column-like typology, where you can see in the middle where the parts were evenly spaced, and on the left, the iterative process redistributes the parts to have a consistent overlap. Here is the image from the final fabrication of these volumes. It's a column and a wall typology, which uses this algorithm, and which is capped with a roofing element to show the even volumetric buildup achieved with this process. Now, in contrast to layer-based additive manufacturing, impact printing allows you to deposit material from a distance. So through testing, we've tried to deposit materials from ranges from 20 centimeters to 2 meters, and this actually allows us for a huge opportunity to embed other subsystems into construction, such as windows, doors. What you see on the screen is is like a replica of different strategies that you could sequence one geometry in different ways, depending on a lot of factors related to material curing and construction sequence. So while it offers these opportunities, there are also some challenges. To embed timber frames, one of the challenges to have the placement of the frame, the other one being the adhesion between the frame and the deposited material, and the last being stability because of the impact forces of the process. So initially, there was a void created in the impact printed volume to physically guide the embedding of the timber frame. And since in most scenarios you cannot construct the whole volume at once, there were separate sequences to always have a fresh layer deposition between the external element and the deposited parts. And then once the parts are, once the timber is embedded, to change the sequence to have an deposition pattern from outside to in to create a stability while construction. Can I say something? Okay. The overall, the global stability is a factor to consider, and because of the impact forces, and to tackle this, there were strategies which were developed, described much better in the paper, such as temporary infills to facilitate tapered structures or cantilevered structures, and which could be removed after. And with the help of these construction strategies and computation tools, we were able to construct all of these prototypes, which shows potential for impact printing to be a valid AM method for earth-based materials.
We can also think back to our original goals, which is targeting a very efficient construction rate. Right now, our cycle time per part is around 7 seconds. We target to increase that to around 2 seconds per part, which is about 1 cubic meter per hour. And right now, we're actually not always depositing material. We really need to basically develop a complete material processing and feeding pipeline. So this is in our next steps. And Kunal is going to talk a little bit more about some of the other research things outside of the scope of the paper.
Yeah, as means to commercialization, we are also looking into robotic finishing strategies. In particular, for my PhD, I'm looking at a novel tamping process, which makes use of the extended workability of the earth-based materials, so that you could tamper it in place, evenly redistribute the material, and have a flat finish. Here are some pictures from the first tests, and proving that this could work, and then the plan for the next few months is to scale this up.
And also in the context of MAS, with 2 of our master's thesis students, we developed another robotic surface finishing method. First, we acquire the surface geometry because it's very textured, and then we use a compliant robotic surface finishing tool to apply a clay-based plaster on the surface. And this gives us a lot of processing possibilities because we can basically take a very cheap infill material, and we can use a very fine, high-quality material on the outside, and we can manipulate the vapor permeability or the durability by changing the surface coating. And finally, we're super excited to announce that we integrated our tool also on the autonomous excavator, which was developed by our partners, the Robotic Systems Lab. We've successfully built a 3-meter tall demonstrator. We're really excited to publish it and release it in the future. And we've also gotten SNSF bridge funding to actually commercialize and take it into industry. So we're moving towards establishing a startup. ChatGPT has not been very successful for us in coming up with a startup name. So feel free to come up to either of us if you have any ideas, any comments about the research, any ideas about the commercialization. And thank you very much, and we look forward to the discussion.
Thank you. Can we go back there?
Yeah.
Thank you, Lauren and Kunal. Just amazing body of work. Next, I would like to invite Bruno Knychalla, who will be presenting functional hybridization through the Breuer XAM project in concrete building envelope components through additive manufacturing.
Okay. Hello, everybody. Welcome to Breuer XAM. In this research, we explore how additive manufacturing in construction can be leveraged to make building envelopes more efficient using geometric differentiation. Let's see if this, yes, okay. This research is a co-disciplinary research of the Transregio 277. The research center is also called Additive Manufacturing and Construction. The first author of this paper can't be here, Julia Fleckenstein, because she recently became a mother. I hope to represent the team well here. My name is Bruno Knychalla. I studied architecture at the TU Munich and at Stuttgart at ITEC until 2017. And then 2020, I started Additive Tectonics, which is an architectural 3D printing company. Currently, we are dealing with the increase of advanced building systems to achieve ever-improving standards of comfort and living in buildings. But those buildings usually, they usually rely on a very complex array of materials that are mostly glued together. Research at the TU Munich has already shown that you can also do this in a monolithic and monomaterial approach. This is an example called Einfach bauen by Professor Florian Nagler. It works in different materials. The prototypical house that you see here, its envelope is composed of one monolithic material, which is here infra lightweight concrete. The lifespan is based basically on this material, on a monomaterial, and it's easily to recyclable because we just use one material, nothing is glued together, and it's done in one construction process. But to specifically integrate certain building functions can be tough in a building system like this. Pioneer architects like Marcel Breuer already envisioned multifunctional hybrid facade systems, building envelopes. In this image, you can see the IBM Research Center in Lagarde, France, which is the base model of our research. Breuer synthesized mainly 3 building functions: building services, installation, and passive solar control in one modular piece. But because of the fabrication technologies of that time, of course, these building elements are all self-similar, or basically the same. So we envision a strategy where we can make one simply built, einfach bauen, simply built monolithic building system, but in a multifunctional way. And we think by using additive manufacturing, we can integrate multiple functions into a monomaterial system and basically increase the lifespan, making it more durable and easier to disassemble. For that, we made a theoretical building, a circular-shaped building, in a co-disciplinary project between TU Munich and TU Braunschweig. Yes, and we said our fabrication technology of choice was selective cement activation. Selective cement activation is a particle bed technology, and it basically jets an activator onto a powder bed. And in the powder bed, there's a cement, basically a dry cement, and the cement hardens. So aggregate and binder are in the powder bed, and just the activator is jetted. Here you see it. While binder jetting, you basically jet the binder. So this is our big future factory at Additive Tectonics. Here we developed a process. We basically scaled up the process to a machine that can hold 10 cubic meters. And this machine can print these 10 cubic meters in around 5 hours, which means that we can produce at the speed of 2 cubic meters per hour. And it also works with construction material. And with the ability to use construction material and these speeds, we believe that we are ready for the construction industry with particle bed additive manufacturing. We developed a completely new material for this because we knew we wanted to have a functioning prototype. So it's based on ordinary Portland cement, and we needed to print a very big part for the first time. The material that we developed was had the density of 1,000 kilogram per cubic meters, and the rest of the material properties point in the direction of infra-lightweight concrete, which meant that probably the insulation properties were very good. We used recycled glass as aggregates from bottles from a local provider, just 5 kilometers away from my company, and 70% of the volume inside this material is basically this aggregate. These recycled bottles get expanded and granulated into different spherical, different sized spheres. And we need these different sizes to generate a nice packing density. And then the Portland cement is added, and also cellulose. We wanted to have a fabrication of a design methodology, so the elements are not just designed for our manufacturing strategy, but also for all of the periphery processes like unpacking and material handling. The design was being done on 3 different scales, while the micro scale was mostly used to integrate most of the functions. In the mesoscale, graphical methods were applied to define the shape of each element. Basically, it defined the position of the glazed area for the different directions. And after solar radiation simulation, we would map a microstructure on top of the surface of the element to basically generate a self-shading on the part, which is more vertical on the east and west side and more horizontal on the south side. Together with the solar control strategies, also structural and thermal functions were integrated. We divided the structural and thermal requirements into 2 zones. Furthermore, dry joints were integrated to attach the elements together later. For the thermal zone strategy, we basically analyzed different cell geometries, and for the thermal performance in 3 categories. Radiation you can see as red, convection in green, and heat flow in blue. The cells vary in size and thickness throughout each element and are thicker where more stress is expected. We did FEA analysis for heat transfer, and different cell families were compared. Basically for the compressive strength and for the U value, and we chose a family of cells that would integrate nicely also with our fabrication parameters. For the structural zone, we had to plan in reinforced concrete, which also interfaced with the 3D printed element through teeth, and also interfaced to the dry joints structurally. Of course, we wanted actually to avoid a second material system. We'll talk about this later. The building envelope was fabricated horizontally and filled in each dimension, and filled our printing setup in each dimension around 75%. And it was the biggest part that we printed by then. And you can also see how deep the insulation channels go. Here you see the printing process. It took us this time 9 hours. We know we can also do this faster, but as it was a new material system, we had to stop sometimes. Basically, water is just jetted and activated. Here you see the unpacking step. This will soon be automated. The print is here still in a green state and can only be transferred with the print box that we also use to lift the print outside of the machine after the print has finished. Now comes a very crucial step. Until here, we basically have an underhydrated cement. 30%. The cement is 30% underhydrated, and we need this because otherwise, when we print with full water, the water would leak through the layers, which would mean that the print would bleed. And also, if the whole part would be activated, like all of the cement, it would shrink, and the powder bed would prevent the shrinking, and then it would lead to the cracking of the part. So here we not just clean it, but also hydrate it. Then the rebar is being put in, and grouted mortar is filled. And after 1 day, you can start to lift the part by itself. Then the part needs to be turned, and the front side is still not fully hydrated, so this is a game against time. If it would get hydrated, if it wouldn't get hydrated, it would also crack. So it's a delicate play of when to put water where. Yeah, but it didn't crack so much. And here you can see the inside of the part. Basically, this you would see from the inside of the building. And here you can see the outside of the finished element. You can also see the thermal zone here. And we also fabricated a smaller part next to it to see the tolerances and to basically see how well the dry joints would work. For my conclusion and for the future outlook, I will separate it again in these 4 points that I discussed before. Firstly, the surface measurements were very successful. The self-shading behavior worked quite nicely and show very promising results. But these measurements should be applied for the whole cross-section and not just for the surface to see how the heat actually transfers through the element. Secondly, we also integrated, we basically had to integrate blow-in insulation that we already knew from the thermal simulation. This had multiple reasons. One reason was the solid structural zone in the back, the varying geometries of the window, but also our fabrication constraints that come from unpacking. So the part at one point was actually designed to be for blow-in insulation. We also used the blow-in insulation because we wanted to achieve passive house standard in the German standardization. A future way to solve this issue would be to trap loose particles inside the element during the printing process. In 3D printing terminology, this is called powder trapping or particle trapping. And this process is basically like a blow-in insulation, and we can achieve this by slightly changing our fabrication parameters. Yeah, okay. Of course, we didn't want to use reinforced concrete. We should avoid this in future iterations, but you know how these projects work. Not everything goes streamlined, and also if you integrate, you have a lot of different functions that you have to integrate. Yeah, but a promising solution for this is design for material separability. And a system like this, I think, can be easily imagined. And I think we can also see some very interesting post-tension systems in some other talks today. Finally, cracking. We have 3 different types of cracking: hydration, shrinking, and part handling. Hydration and shrinking are actually come from the same root. Both are based on cement, on the behavior of cement. If we use larger particles, we need less cement inside our parts, which means we have less cement that will shrink and that will also dry out. So by using a bit larger particles, we can steer these problems into we can, I think, handle these problems quite nicely. For the part handling cracks, it would be necessary or nice to integrate fibrous materials. And For example, like in our novel material, which is called EcoNeat wood, we use fibers from residual wood waste. And if you're interested in the developments that we do on wood 3D printing in powder bed system, you can scan the code. We will reveal this material next week on the Milano Design Week. I want to remind everybody that this is a material agnostic process. So we are open to different material possibilities. For us, it's very important that we are able to print with them. But the material system, I believe strongly that we can make a material system that in the end can be considered carbon neutral or be considered a carbon sink. This research was funded by the German Research Foundation and under the Collaborative Research Center Additive Manufacturing and Construction. It was a great pleasure for me as an industrial partner to be part in this, and I think we were also great research partners in the end. I want to thank, first of all, the FABRICATE 2024 team. They did an amazing job. And I'm very sad that Julia couldn't be here. If you have any questions, let her know. She also said I should tell everybody to connect on LinkedIn. So then I want to thank all of the professors that are involved and the whole TRR 277. And of course, the team at Additive Tectonics that did all of the heavy lifting and heavy work. If you're interested in what else we do, or if you're interested in joining our team, we have some open positions and internships. Thank you.
Thank you, Bruno. Amazing work. Next, I would like to invite Mariana Popescu, who will be presenting KNITNERVI, Lightness and Tailored Materiality for Flexible Concrete Construction.
Thank you for the introduction, Jenny, and thank you for having me. I'm here to present KNITNERVI on behalf of myself and the co-authors, and I wanted to highlight that because this started as an interdisciplinary project at the Block Research Group and NCCR at ETH, and it magically turned into an international collaboration because I moved to Delft. It very much bears the heritage of being sprung up from this, from the BRG and NCCR. The background for it is that in current construction practices, reinforced concrete is overused because we usually rely on it deriving its strength from using a lot of material, so overuse of material. In contrast, if we use informed geometry, structural geometry, rib-stiffened geometries, and compression-dominant ones, we can achieve more or less the same type of result, but at much less material cost, so using a lot less material. Unfortunately, when we look at how these structures are constructed, although pioneers have looked into how we could do this rather beautifully, elegantly, and efficiently, we find a question of complex formworks that are difficult to manufacture and usually hinder the adoption of such structures in construction nowadays. As I mentioned, through that heritage, we usually look from the BRG in that sense. We usually look towards the past and towards master builders or ones that were intelligent in how they designed their structures. And that's where this particular pavilion also comes in to showcase a particular way of constructing for concrete structures with a lightweight, flexible formwork, as opposed to the usual traditional formwork technologies that we used. In this particular case, the flexible formwork uses a knitted textile, and the way that works really quickly, as shown in other projects, it's by manufacturing a knitted textile, tensioning that into shape, coating it with a thin cement paste or not, depending on the project, and using that to cast concrete. And once that concrete is cured, the frame that was used to tension this type of formwork can be removed and the structure can be revealed. Now, although this usually does mean that there's a significant reduction in the type of formwork materials and the waste that we have associated with that, we still need quite a lot of framework or means of tensioning these types of textiles into shape. So we tried to also make a further step or an evolution of that type of system in which we would not rely as much on external non-reusable frames for the project. Now, as the name might suggest, KNITNERVI is inspired by the works of Pierluigi Nervi, and particularly by the Palazzetto dello Sport, because it was built at the Maxi Museum in Rome and roughly a couple of hundred meters from this beautiful structure, the ribbed dome of the Palazzetto dello Sport. So it echoes, or it takes inspiration from that structure, and tries to come a little bit closer to something that perhaps industry might recognize as something that can be implemented in having reinforcement cages and some of these types of geometries that are a little bit more recognizable than purely doubly curved shell structures. In this case, and you'll see here how that diagrid shell was set up, what we set out to do is have an integrated structure and formwork system whereby the bending active rebar cages that are built up as a scaffold for the knitted shuttering become an integrated part of the structure once concrete would be cast in there, thereby avoiding the need for any other non-reusable tensioning components. The only components that would not be part of the structures are the pillars that you see at the bottom, which are used during construction, but those are usual standard construction props that might be used in any other type of construction afterwards. Now, as a disclaimer before we go forward, because you've seen it on all of the other images as well, we haven't actually cast concrete in this structure, but we have used it as a showcase for how a lightweight formwork with integrated structure can be added to it. The process started by having it's a form finding process to get our general geometry for the bending active splines. It looks something like this. That geometry, which inverts the system of the dome by bringing a tension ring up and having the diagrid formed by splines in two directions overlapping each other. These are actually in a triangular section connected by stirrups, and those are then used with 3D printed profiles to hold up the knitted shuttering outside of them. To give you a glimpse of what that might look like as a system, the easiest way to do it is actually with a picture from while it was being built. So on that image, you can actually see the rebar cages and the knitted textile being tensioned around it. And the places where we were considering casting said concrete would be within the diagrid itself and no further. Okay, that's it. The construction stage was done in two big chunks, let's say. First, the prefabrication and the construction of the grid shell. Part of this was prefabricated in Zurich, like the rings, the inner and the outer ring. These were then transported to site and easily assembled as a kit of parts with construction workers, so actually in a context where we as researchers don't necessarily do all of the work. And you'll see here how those splines are being added in clockwise and counterclockwise direction to the structure, and then tied together to form the rebar cage that is a grid shell. Now, part of this is also making sure that we reach the geometry that we want, very carefully measuring all of the intersection points. And you would have seen Lotte, the one that has actually designed and calculated the grid shell, carefully checking that everything is placed exactly where it should be. So in our first stage, we had this structural grid shell that becomes reinforcement within the structure. And we took advantage of the fact that we have a little bit of time and decided to take that time to measure the constructed geometry such that we can build a fitting textile, not for the design itself, the original one, but for the measured in structure, because we had a computational pipeline that allowed us to do this relatively fast, meaning that we didn't need to start production in parallel with having built the previous structure. I'm going to focus most of the presentation on the computational pipelines for the knitted textile in this sense, because the project doesn't only deal with the part of global geometry, so having that architectural geometry or structurally informed geometry that allows us to reduce raw material use and perhaps reuse, and I can talk about that because we haven't cast it, but also about local geometry and how we might be able to control the material properties and locally on that textile, which allows us to introduce functionality and architectural expression in certain places. So what you'll see here is actually a more or less zoomed in or detailed picture of the textile as it was assembled. And what you might notice, besides the X-ray through the structure type of view where we can see the rebar cage, you'll see that the diagrids in between, which were not meant to be structural or cast in concrete, have a very specific texture with different densities that can be manipulated and controlled during production. Now, to do this, we segmented the geometry in 74 parts. This was for production purposes, but also for being able to generate the production files accordingly, because it entails some computational weight in case the pieces are too big. To decide on the density or the porosity of our and the expression of our membrane, what we did is we started with a density distribution of where we wanted to have a more closed and more opened expression, and divided that into different zones that would then control the amount of openings that we use on that particular side. That was also superimposed on the ribs that you see there, and for each one of the parts, a knitting pattern is generated on a 3D surface, which entails about a little bit on the generation of about 30,000 points for each one of those strips. So having 74 strips kind of gives you the idea of the magnitude of the computational step that needs to be done in this case. Now, we take that type of generation, and actually each one of those points that you see in the 2D representation of the pattern represents a grid of 4x4, so it actually represents 16 units within the fabrication file, which has specific operations that allows us to introduce that porosity. That means that in the end, in terms of production, that's about 500,000 points that we needed to generate in this way, which means that we needed to have a post-processing step directly on a bitmap. So each one of those little pixels you see there that turns into those 16 comes from a piece like this that then gets processed into a bitmap that looks a little bit like that. And this is then further processed to add those densities based on our color gradient, so our darker or lighter shades of gray, to have those openings within it. And what we are left with in the end are all of the instructions that we need for the machine that have all of the different operations in exactly the right place. So for the second step, those instructions are fed to the knitting machine so that it can produce those 74 pieces that very conveniently and lightly fit still within a bag, not for the rest of the oh, that stopped at the wrong place. But there was a bag at the end of it, I promise. And we went on site in Rome, where we found our beautiful steel structure, and we started off by hanging the ribs that were to form the clockwise and counterclockwise direction, and then slowly start putting also the top surfaces on. So you'll see that this is not necessarily a completely sequential process, so we can do some of these steps at the same time. They don't require very specialized skills, sometimes just one person on a scaffold, with unskilled labor at that, that can put together this kind of lightweight system that ends up in this. I have here a few impressions of the project once it's realized, and what you'll see is that we, by not casting concrete, what we did is we made a lighter textile that gave the visitors an opportunity to have an X-ray through the structure, so understand how a concrete structure might work. But we also took the opportunity to make it completely demountable, or look at the possibility of having that demountable. It has been demounted, it has not been reassembled anywhere else, and probably can't be. But we did have that intention to have it completely demountable. Finally, what we need for that basically is to have, on the one side, the possibility to create these types of efficient deployable formworks, both at the global geometry level, but also graded materials. And we need for that both computational design, but also computational fabrication pipelines. And these need to be scalable ones, because if we start from the first prototype that was about 50 square meters, this one looks smaller, but it is roughly 3 times the size. And because I keep finding myself roughly every 3 years somewhere on a scaffold pretending to be a construction worker, roughly every 3 years the surface area also increases by 3. So yesterday I came in from Bruges, so I'm going to leave that out just as the last thing, where these types of computational pipelines helped us generate something that is 370 square meters in the same amount of time that it originally took to generate that for the Knychalla. And with that, I would like to thank you, and happy to have a discussion afterwards.
Thank you, Mariana. Really incredible work. And our last presentation will be by Leslie Locke, Sasa Zivkovic, and Fabian Meyer-Brötz. And they will be presenting House of Cores, advancing collaborations between building industry and academia to develop integrated, applied, and resource-efficient models for housing construction.
Thank you, Jenny, for the introduction. And we're thrilled to gather here today at this FABRICATE conference and presenting along this collection of incredible projects that we just saw on addressing the question of building integration and context. And so for our team, deep collaboration across industry, practice, and academia is pivotal as we strive to address global resource challenge and begin to co-developing integrated, applied, and eventually resource-efficient models for construction. Sorry.
Big green one.
Just one, okay. And so our presentation is structured in 5 parts, outlining several research and development aspects of the project. And my name is Leslie Locke, and I will be co-presenting this project along my co-author, Sasa and Fabian. The research project is a result of a multi-year collaboration between HANA and Experimental Design Office with ties to our Cornell University labs that led the project's design planning and coordination, as well as Perry 3D Construction, a global leader in 3D printing and advancing 3D printing solutions in this project. And third, CIVE, a design-build innovator from Houston who led the structural engineering and is also the project's general contractor. And so the project, just a bit of a context, expands on prior full-scale additive manufacturing work, research that are developed by the authors here, such as HANA's Ashen Cabin, presented at the FABRICATE 2020, other projects including additive architectural elements and the Rolling Stones, each probing the technical, conceptual, and design implications of the technology, as well as projects by Perry 3D, printed in Beckham House, the first 3D printed house in Germany, a 2-story concrete structure with 3D printed load-bearing walls, which then demonstrate the feasibility of this technique in the German market, which has led to a number of applied research projects across various scales as well. And so for us, the House of Cores illustrates the possibilities and current challenges of in situ 3D construction printing technology, mass customization, and design solution that integrates conventional construction methods. So this project served as an active testing ground for us, where we looked at 3D printing process and logistic optimization, material sustainability evolution, innovations in design and mass customization, as well as a mix of a series of on-site and also off-site 3D printed construction in this project, combining with hybrid structural innovation and also integrating the various associated trades, and most importantly, permitting and on-site inspection schedules for a residential building in the city of Houston. And so first, where we start was we were looking to respond to the residential building practices in the United States. House of Core is designed as a hybrid material structure of concrete and timber framing, establishing a flexible construction system that can be readily adapted to multifamily housing in the US market. The main spatial organization principle here establishes a series of 3D printed load-bearing cores connected by lightweight wood framing for floor, ceiling, and non-load-bearing walls assemblies. And as you can see in this plan here, the printed cores, essentially there are 5 of them, contains functional aspects such as bathrooms, storage, staircase, HVAC rooms, seating nooks, and so on and so forth. And between the printed cores and the frame walls is to generate an architectural and spatial alternation of concrete and wood walls with glazed infills, bringing in the mixture of light and heavy materials. And so the printing process is familiar to most here in this audience. Is, as we know, a delicate balance of rheological parameters, material compositions, printing speeds, layer times, flow rates, and environmental factors such as the blistering heat in Houston, Texas, which in one summer, I believe it ranged from 38 degrees Celsius to 42 degrees Celsius. And so key parameters for our project were consist of layer height of, because we're in the US, 0.75 inch tall and layer width of 2.25 to 2.5 inch width, a maximum cantilever angle of 10 degree, and dilating corner radii between 3 inch to 5 inch. And also using the centerline tube path calibration for start-stop positions during the printing process. And so for us, balancing the tube paths and the printing parameters on how the line begins and how it ends and this radius turns into a feedback loop between design refinement and on-site test printing. While we all know that the filleted corners and larger radii are easier and faster to print, they can present challenges for connections and the integration of other building systems. So as a result, the project back and forth was very much in a constant negotiation between the machine's technical means and also the project's architectural ends. And you can see here on the interior, we highlight the design potential of mass customization architectural components through its programmatic nukes and filleted undulations to create a series of spatial sequence of concrete thresholds. And the layers of softly curving concrete reveal different customized storage spaces, lightings, vessels, and also bookshelves later on for the building's users. On the exterior, the facade of the 3D printed wall is prominently characterized by a series of small steppings. They're meant these 10-degree cantilevers that seeks to break down the massing and the volumetric shifts of the concrete walls through this gentle corbelling.
So while the printer is relatively easily able to generate custom geometry, conventional building systems are not yet comprehensively ready to take full advantage of the printer's ability for mass customization of geometries. And this adds to the existing challenges with detailing, structure, but also building integration design. So to develop a permittable residential building, our team had to collaborate and develop integrated detailing solutions that enable the interface of various systems, taking into account construction sequencing during printing, the integration of trades, inspection schedules, and the printing process itself. And so in this animation, you see the sequencing and steps necessary to execute the project from the foundation to the concrete rods that get into the foundation up to the second story. So in here you see the various rebar systems that we had to develop for the project. So there's rebar cages for bond beams and bond columns. that were inserted during the printing, after the printing process of the first level concluded. There's an inner and outer shell that's connected by U-ties, and within some of the cavities of the concrete infill wall, electrical systems embedded into the system itself. And because it's a two-story project, we had to also carefully think about how we make load transfers possible by printing on top of these bond beams and bond columns. And the system essentially repeats on the upper floor and tops out with a parapet. Oops. So the project developed three typical wall types using mainly 3D printed double layer wall systems with insulation cavities and integrated bond beams. The second section shows the 3D printed double layers with the reinforced and cast in place concrete. And then the exterior layer, as you can see on the right, connected with U-ties, inverted U-shaped rebars to each other, as well as to the foundation. One of the biggest challenges of 3D printed projects is the integration of reinforcement systems that don't interrupt the efficiency of the 3D printing process. So in this project, structural reinforcement, as mentioned, is placed in the cavity spaces at the conclusion of each layer to perform the bond beam structure and bond column structure. There's some additional details. The exterior 3D printed wall also has steel reinforcement that follows the geometry of the wall. This reinforcement is placed between layers in 1 foot increments. And you can see one of the Perry team members integrating this type of rebar during the printing process. The printed walls themselves are insulated using two new closed cell foam insulation system with a high recycling content from Huntsman Building Solutions. And that is then paired with an HVAC system to regulate interior temperature and air and moisture content. And so with the cores completed, we are about to start phase 2 of construction, which includes the conventional wood studs and trusses for the floor and roof slabs. And the floor and ceiling system consists of wooden trusses that are attached to the structure using ledger beams and joist hangers. So this is where the 3D printed structure interfaces with the more conventional building systems that we find in the US. And the aim of this project is to take advantage of both of these systems in this hybrid assembly.
And now from an industry perspective, what is then always important to us in the end for the mass utilization, where most of the CO2 that we're talking about is being utilized, is in the end it's all about cost and time. So we weren't looking at creating a completely new process or a completely new computational model, but taking a lot of smaller incremental steps to bring down cost and time over the course of this project. One of the core things here, it starts with the site. It's a very typical suburban lot, so it's very small and it's very long. So we had to make sure that everything is placed accordingly so that we have an efficient process down the line. I'll skip ahead slightly and for the sake of time. So the building was printed in several sections. One section with the first core and a chimney that was also printed with precast pieces on site. And then the printer was actually increased in size for the next two sections that were printed afterwards. And between those sections, we always took a little bit of a pause to review and think about what had we done, what can we improve overall in this process. And there were a lot of things, but I just want to highlight a few of them. One was that we had integrated a water chiller/heater to deal with the Texan heat and wind in particular. So for all of you guys that print indoors, if you go outdoors, it's a completely different ballgame. And that was a very important learning journey here. And how do we navigate that? How do we include sensors and cameras so that we can monitor everything on the fly, adjust it on the fly, don't have workers standing outside in the brutal Texan heat all the time, but have them nice and comfy in a site office. Cracking is, for all of you that have printed concrete, an issue, but here we've dealt with it in several ways, where we included expansion joints that are very important in the 3D printed structure, as well as you're using different curing techniques, as well as should, after all, a crack form, we had certain mitigating measures to ensure that the crack doesn't propagate through the structure. Another point is the scaffolding. Well, if you go up 2 stories, you want to not just make sure about the sustainability, but also of the safety of your workers. So you need to put up a higher scaffolding. Unfortunately, the scaffolding can also be in the way of your printer. So if the crew that puts up a scaffolding hasn't ever seen a printer before, they will 100% set it up in such a way that you cannot move your printer anymore. So a couple of iterations later, you then will have a scaffolding that is actually being able to use it in a sensible way. And here we really highly recommend to not just model whatever you're printing and not just the machine, but everything that goes around it. If you use a ladder, put it in your 3D model. It will help you a great deal. And so all of those strategies that we have implemented had actually led to an increase of productivity by a factor of 2, at least almost, where initially in the first couple of months we had roughly 12.9 tons of material printed per week, and in the end it was 21.5 tons, always depending on also the other processes that we had around the structure.
And so to wrap up, we acknowledge that there are many more additional incremental steps that must be taken to advance our construction practices, especially in the context of sustainability, operational carbon, and embodied carbon. And developments are moving fast, and since the House of Core represents, for us, a small steps toward more sustainable construction with concrete, first, the wall assembly in the concrete cores ensures no thermal bridging, as you can see in one of the images here, between the outer and inner print layers, and this results in a thermally efficient building envelope, which can then be flexibly adjusted to meet and or exceed building code requirements. And second, in the course of the project, the 3D printed material was reformulated and optimized. So while we print, we keep improving and fixing our process. And we can expect further material advancements in the near future. Noteworthy in this project is that the maximum aggregate size used in the material formulation was increased from 4.5 millimeter to 9.5 millimeter, moving from initial the mortar base to real concrete printing. And so third, and in a way lastly, we have to continue to ask ourselves, what do we print and what do we not print? And in this project, the use of concrete was limited to the load-bearing structures only, and it emphasizes was placed on the construction system's hybridity. And so this project was deliberately structured horizontally as opposed to a vertically integrated manner to bring in knowledge and expertise through the variety of stakeholders. And so, however, there's a vast amount of smaller issues, and in particular, the integration of the various trades involved in the construction industry of a residential home is what currently keeps the construction industry from adopting these new digital fabrication for real impact. And so moving forward for us, we hope that the academic community could direct more emphasis to applied and holistic building process research for residential construction. So in simpler words, we have to get to the actual building. And so together, House of Course, varied design strategies aims to move the needle a tiny bit towards increased impact, applicability, and eventual cost efficiency of 3D printing for future residential multifamily buildings. Thank you.
So please join me in a round of applause for all of our amazing presenters. And I'd like to invite everyone up to the stage. Need one more? Okay. There we go. All right, so we've come to our Q&A session. And I have a few questions to kick us off, but I'm sure the audience also has a number of questions. I couldn't help but notice the suburban Houston context surrounding House of Cores. And maybe the first question I'll kick off with is, how do all of you and your work manage standardization versus customization, and how does that impact or benefit or perhaps hinder your collaborations, as well as identifying resource efficiencies?
I can start,
Go for
maybe.
it. Yeah.
Well, because we're starting to look towards the goal of commercialization, I realized that the added value of customization is zero in the minds of investors. Basically, we need to deliver a product that's competitive with, straight wall sections, and if we can't achieve a benchmark cost that's similar to straight walls, no one's going to pay more for the custom walls. So for me, it's about starting from the cost of the standardized elements and the things that are built through the logic of serialized production, and then thinking backwards and saying what is the throughput that we need to achieve competitiveness.
Mm-hmm.
But it's maybe a very
if I can jump on what you said, I think actually the way I experience it is that the only reasons they're not really adopted or jumped on is because we cannot guarantee the same type of quality assurance with a custom system for the moment as we can with a standard one. And that means whether we understand the material properties of a 3D print and whether they need to be simulated, computed, understood. So it's mainly a gap of not understanding what we're producing yet, or not being able to guarantee those in the same way.
Yeah, I think in the context of our project, negotiating with the standardized portion also comes in terms of building codes. So for example, how concrete structure is evaluated, where there's a minimum monolithic thickness that needs to be achieved for a concrete structure, and that also becomes a parameter that we need to respond to the width of the print line. So if we were to be a double line, then that would meet the building code for a concrete structure. I think also in terms of the customization part, where we develop a double layer wall, that cavity becomes something that we can easily dilate and customize in the design. So whether if we're going to build for context for Houston or versus upstate New York where we're based, the thermal requirement is entirely different. And so that's where we find also opportunities for the flexibility of a mass customized strategies.
Yeah, I think it is insanely complicated to make a custom element that is competitive in price to something that like a product or something like a standard product, because if something is bigger than you and you have to handle it or somehow be responsible for it, you need to put engineering in it. You need to put this extra work into it. And if it's customized and you need to do this every time, the costs explode. And this is why I also think in a 3D printing perspective from industry, there are not so many products that are actually 3D printed because of that reason. You can't always recalculate everything. Not even Adidas managed to do it with their shoes. So I think a lot of it is lacking computational power, lacking processes that are performative enough to do that. And the other part is the responsibility that's being put on industry. Like you just don't really want to do it in the end, because it's a ton of pressure if you do something for the first time and it needs to be right.
From the industry perspective, again, in the end, it's all about cost and time, right? No matter what we tell ourselves, and we didn't believe this when we started this process a couple of years ago. We thought, look, when we can do, and then I'm oversimplifying here. I'm a physicist. I'm not an architect, so I'm gonna piss some people off. But we said, all right, if we can do those fancy designs, people will run in our doors because all of a sudden we can do them at little extra cost, right? The fact is that didn't happen, and now with the spike of interest rate, it didn't happen times 2. And the majority of the buildings we build worldwide are single-family homes or smaller multifamily homes. That is the truth of it. It's not pavilions, it's not halls, it's not airports, but it's single-family homes. And if we really want to have an impact on all of that, from a CO2 perspective, from a planning perspective and engineering perspective, then that's what we should do. All the rest can only be, from my point of view, an intermediate step. And then the mass customization needs to have is a means to an end, including of openings for electrical outlets, and you can make those very individual for each single project, and the windows can have a specific size, all perfectly fine. But it's then the means to an end to achieve better cost and time performance, and not necessarily because of the aesthetics of it.
Yeah, I wanna add one more point to this conversation, and that is the notion of material resourcefulness and structural efficiency. That is an embedded potential in some of these processes. Admittedly, this is not what's driving the house that we're printing in Houston. That has to deal with other realities of building code and implementation. But I think the fact that the 3D printer or any digital fabrication device can be resourceful and responsive to structural requirements, to reduce material where possible, and to deposit only material where necessary, is one step or one important potential of it. And if we combine this with conversations that we've had this morning about a potential CO2 tax or something like that, these kinds of savings become valuable potentially, right? And so this goes also back to Bruno's optimization of surfaces for shading purposes, etc. So I think with the computational pipelines, with the responsiveness to environment and structure, there is a lot of potential to be still utilized and kind of left on the road so far.
Yeah, I also wanted to say that I think customization is great in areas where there's not a lot of responsibility. So, for example, surfaces or openings, or but if you have some type of catalog where you already thought about each element once at least, then it becomes much easier to offer customization.
Yeah, I think we did discuss or went through this discussion some time ago. I think it comes down to who pays for this customization, right? Is it from the service provider side or it's from the client? Like in the context of Switzerland, I think out of 1,000 houses, there would be maybe a case of one who would prefer to pay extra to get this added value. So if we can't match the costs for mass customization with mass production, I think people would still intend to use the mass-produced stuff rather than customized products.
Yeah.
Well, maybe related, I'll open the next topic up, which Lauren, you brought this up in our discussion, and I grappled with it over the last week. But I'm curious to hear all of your thoughts on, does fabrication need an academic home? Do we need a new field?
Well, what I think is interesting is that in Germany and Switzerland, architecture is at least treated like a technical discipline, which makes it competitive for engineering-based funding, and that's maybe why you see a lot of innovation in this context. But at least in the US, this is a big problem because architecture, there's not equivalent funding schemes, so you can't achieve the same in terms of research effort that you need to actually push results. But at the same time, it's a disciplinary, I think there's huge value in being a generalist, but academia is domain specific and privileged specialization. So I think there's a bigger paradigm shift in addition to the way that funding structures are handled that enables generalization and treats it as being important, and also enables design methodologies to be as important as engineering quantifiable methods of development.
Thoughts?
If I can offer a perspective on whether we should be another field, I don't think we should be another field. I think we should be a little bit of a disease spread all over the other fields. Just
like that.
A little bit here and a little bit there, and being the fact that it has primarily found its house or its home in a architecture environment is perhaps because of the openness and creativity and ability to or willingness to think outside of the box. But if we infiltrate the other fields, let's say, then there's more opportunity to start building those bridges and to have that type of thought in other domains as well, and bring in that kind of conceptual creativity, perhaps. But what that would ultimately do is it won't turn an engineer into an architect, and it won't turn an architect into an engineer, but it will give them common ground to discuss and start integrating things a lot earlier and understand each other when they say design. Because when an architect says design and when a civil engineer says design, they're two different things. So we shouldn't be on our own, but we should just be.
I mean, it does help when you look at a problem with different disciplines, like with the eyes of different disciplines. If you look at fabrication from an engineer's point of view, it would be just enough to have the things there and functioning. But as for an architect, as you mentioned, it's a lot more. I think we also care about aesthetic appearance. Then there's a lot of, let's say, liability on how the structure would be used. So usability is another case. So I think it, or at least in my case, things changed when we started looking at architecture from different eyes, like from different fields. And this kind of brought the change to where we are now, or where we're heading, probably.
I think it clearly needs to be academic, because coming from I have a bit of a background in industrial fabrication, in basically industrial 3D printing, and there you basically have the problem of just creating this form with all means necessary. And if this problem is not in any way dealt with academically, you start to just do it in the most simple or in the most direct way possible. But in the world that we live in right now, we can't afford this anymore. So we have to go there with like a broader, like all parts of fabrication need to be dealt with in a more academic sense. In Germany we have apprenticeships for this, which help a lot in the physical part of it. But sometimes, the greater scheme of things needs to be addressed. And I think fabricators have a huge responsibility nowadays. And in my opinion, we should push us even more in the direction of classical architects, because I think it brings back together this building masters, digital building master that is necessary today.
I mean, it's an interesting question, Jenny. I've also been thinking about it since we've had our conversation, and I do think though, at least in the US context, we need more funding for applied research that integrates holistically and synergistically across a number of disciplines, and I think that's there isn't enough available funding in that realm, which hinders collaborations at times, but also the development of works at a certain scale. In terms of disciplinarity, I quite enjoy being part of the architecture disciplines because of the generalist notions of it. And maybe there's a sort of specialization or a bias towards digital fabrication and design, and then in our case, work in concrete 3D printing that we showed today, but also in robotic timber fabrication. But what I do think is that these are not only technical discourses, which is why I think it's actually important to still situate them or to sort of approach the topic through the lens of a generalist architect, because there's sort of broader questions of politics, society, etc., where sort of our connections to the humanities can be leveraged and also play a big role in shaping this discourse, or also maybe changing the way we might think about this discourse more broadly.
I have another question, but maybe I'll pause and open it up to the audience. I'm sure there are some questions.
Hello, I just wanted to ask you about what do you think, like the motivation of the academy into understanding the development side, the developers side of the situation. So about the cost of the materials and or like making things more profitable and more marketable. So like, it's usually the talk is about making like taxes about unsustainable materials, but what do you think there are chances to make developers getting more interested into having like cost-efficient sustainable materials or more marketable? It's like the medical industry, there is a demand all the time, but it's the other way around, like development is interested in cost-efficient stuff. So thank you.
Maybe I'll start on that one. Maybe a short question in the realm here. Who comes from industry, let's say developers or contractors? You see the problem at hand, right? So it becomes quite obvious. But I think, again, right, that it depends on what we build. And the majority of what we build, that is then what needs to be tackled. And in the end, to how do I put my insulation in it and my waterproofing, and how do I hang a picture on the wall, and all of those things become relevant. So all of a sudden, a simple structure, like a simple dwelling for affordable housing in the Philippines, becomes an exceedingly difficult project to build in a fabrication realm. So if we only focus on let's say, a load-bearing structure, we're missing significant portions if we want to create shelter for the people. And so I feel, actually today I was quite excited that we saw with the knitting exercise that it was not just one iteration, but we now saw a second iteration, right? And I think it's great that such a paper was selected to be part of the stage. And I would hope that we see 5 more of those iterations. That all of the clever people in this room and all of the PhD students and aspiring students that are here are being incentivized to do this type of research. Not to the next cool computational thing, the next cool 3D printing stuff, but this iteration, bringing the cost down by 50%. And in other fields, right, usually, as you said, medicine, you'll have some researchers, they do the fundamental research, and then somebody from industry will pick it up, because they have this R&D money. The construction industry doesn't. Barely any R&D money in this industry. And so just to say, well, now it's the job of the industry to pick it up, we need to say, well, this is a very special industry, and there's good reasons for it. We sometimes say it's difficult to move and it's not innovative enough. Who has seen the SpaceX launch not too long ago? Somebody? Yeah? So the rocket came down and it exploded again. It was almost 100 million gone. What was the media's reaction? Great success. We learned a ton. Now imagine we build a bridge with a completely new material. We use some knitted formwork. First car drives over it, crumbles. Nobody's going to celebrate that, right? And so the construction industry has some challenges, and now we need to, and I'm part of it. The industry needs to move, right? But I believe, and this is maybe what I want to encourage all of you, you need to move as well. You cannot treat this like it's medicine or pharmacy, but take the next step. So the next FABRICATE papers, at least a portion of them, maybe it's basically the same paper as we've seen already today, but the process has been improved so much that it's now 50% faster and 50% cheaper. And so all the reviewers in the room, I can only, again, encourage you to not say, well, it's not novel enough, that's not going to have a space here, but to actually say, well, that is what has a space here. Because again, all those clever people, we need to incentivize them to solve these problems, take a step towards industry, and then I think we'll come to where you wanted to be.
I feel a little bit we're talking about the difference between radical innovation and incremental innovation. Mm-hmm. And like you said, construction industry has very little R&D funding, so we can't expect industry or radical innovations where you have many dependent technologies that depend on each other. You can't expect that would ever emerge from industry itself, whereas industries that have more money, more margins, they would, let's say, have more breakthroughs through R&D, through industry. Whereas with architecture, blue sky research, we have the ability to put money into knitting, and then you might find that it has an amazing application and scenario in the future. And that is based on blue sky fundamental research, and then finding that niche where it could make a difference in terms of an application scenario and be, let's say, optimized over time.
I don't think the comparison with other industries is as fair, because it is true that the construction industry doesn't have a lot of margin because it operates at very little margin, correct? But also the time process of getting a building or getting a bridge or getting whatever it is very lengthy compared to any other industry, right? So you can't really just say, well, okay, let academia come closer to industry because industry doesn't have the money. Industry doesn't have the money, but it also needs to open up a little bit. And you are here as a testament to that, but you're one of the few. That's so there's and that has something to do with how we educate people that end up in industry as well.
I also believe in a top-down approach there. I think if we as a community kind of stick together and help each other, in research as well as in industry, and basically collaborate on bigger projects, the question of costs is a bit of a different one, because we've seen from the past, like with ETFE membranes, like you have a top-down approach. Like first you build a stadium, and then slowly you go down and think about when to build a single-family home. Because to bring down costs, you need to scale up, and it's very weird to scale up without a project. Like I can't just say, okay, now we need to build like a, I don't know, 10,000 square meter hall or whatever to have a working perfect concrete 3D printing process or alternative material 3D printing process for construction. But if there would be a project and people would be willing to invest in building this up during this project, and some projects are big like this, like stadiums are big like this, and I think architects have the power to push this, and I think a lot of you will end up in positions where they can influence it and steer it. The problem is it might be too late by then. So we are still a very young discipline. That's our biggest problem. All of these deciders, they have a certain age, they sit in certain areas, and I hope that we can accelerate this by staying as cool and as innovative as we are. Yeah.
Yeah, and maybe also circling back to the points that the interest from developers, and in the US there are actually indeed a lot of developers that are interested in additive manufacturing, and they're buying the whole 3D printing systems, right, set up from Perry, for example, but also many other 3D printed companies. And so developers are actually also driving the market by setting up their own system and pipeline, and they are then using these tools in building or developing architecture or these housing developments in a very specific way that maybe have different consideration that we are concerned about, whether it goes into sustainability, material resourcefulness. So they're using the tools and considering their important aspects such as construction costs, square footage costs, and so on and so forth. And going back to then Jenny's question earlier, and it's even more important for us as architects and designers and researchers to be in this space so we can actually also drive and influence, have a say on the future of these construction methods and futures.
Is there another question from the audience?
Thank you. I think this topic is very important from the stance of academia and also the industry. Since you're all coming from different, let's say, backgrounds and contexts, I wanted to ask whether you have any, let's say, strategies or models for obtaining the research integrity when you're working with different industries. Is there like a struggle to basically maintain the path of your research that you wanted to initially take? And are there any, this is also related to the intellectual property rights and things in that domain. So are there any successful, there probably are, of course, but what are successful ways of basically regulating those collaborations?
Yeah, that's a great question, and a tricky one also. I mean, I think generally good collaborations are based on trust relationships, and so that plays a big part in it. And good collaborations also take time. It takes time to build the networks. It takes time. It took us so long to, for example, figure out the contract structure for that house in Houston. So one has to have the kind of willingness to invest the time. This is one way to think about it. I think one of the reasons why we're collaborating with Perry is because we kind of share an open source ethos to a certain extent. A lot of the work that we've done at Cornell, the 3D printer that was developed at RCL, for example, that's an open source machine. All the information on how to build that machine is out there. And if someone wants to know more about it, feel free to contact me. And in similar ways, for this project, we're open and transparent about, we share architectural building details or details of things that went well, that didn't go well, and we're trying our best to self-assess while we operate. Now, of course, there are certain sort of IP-related topics that have to be navigated, and that's, I guess, mostly kind of project dependent.
I also wouldn't be too worried about any IP issues, at least. So in a young industry, if you're the only one that does it, it's never going to work. Nobody's ever going to believe it. If only Tesla would build electric cars, we would never have the charging infrastructure in place, right? So competition is, particularly in the initial years, it's actually not competition, but it's partners in crime. So to share knowledge and be open and transparent about it, and if somebody else then copies it and does the same, it's only going to push the thought itself forward, right? So the more digital fabrication elements we see, the better. And so the more we share, the better, the more open we are, the better. And there's, I mean, all the material providers that I know in this world, and the contractors and the developers, I mean, they all want to. It's not a matter of that they don't have a wish for change. They also see the need for change. And so I think that there can be ways to collaborate with them. Yes, you might need to accommodate certain things, yes, but in the end it's going to then, I think, create more value.
I think IP becomes a very interesting topic when you need venture capital, because people will ask you which parts of the IP are on your side, which parts of the IP are somewhere else. So there, you should prepare for that. If you work in a university, it should be clear who owns what, purely for this case. Later, it is different. I felt in the construction industry that there are certain clusters of people, and they are divided by material system. Like the wood people are completely different than the concrete people, and they don't want to talk to each other, and blah 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 blah. So for us, as somebody that is material open, that was a weird situation to be in. There, I think it is time that the industry also comes together and treat these problems as one thing. And then, if you work together with the wood people, the concrete people might not want to talk to you anymore. So that makes IP and these research projects a bit problematic. I don't feel like it's like this in research, or at least I hope so.
Meta has a question.
Hello. Yeah, I noticed that in the project of impacted printed structures, the random model is very homogeneous. Considering the collapse degree of the material, will there be some errors between actual construction and the design model? Will these errors be considered and compensated for during the design pass?
Sorry, can you repeat the question?
Yeah, I believe the question was, if the material isn't quite as you wanted it to be, are you adjusting your printing process on the fly? I hope I translated that more or less okay.
So I think one challenge is that we're trying to use a byproduct, and the byproduct has variability. So it has variability in the fines versus the aggregate versus other components. So ultimately what we want to achieve is an adaptive mix design that still achieves the same mechanical properties every time. We know that our mechanical properties are a little bit lower than unreinforced rammed earth, which is around 2 megapascals. I think the challenge is what are the mechanical properties that are needed for the building method, and how do we link that to the fabrication parameters? So we know that our most important parameters are the yield stress and also the interparticle cohesion. So maybe, Kunal, you want to say something about?
Yeah, I mean, I can mention it from the perspective of our project. I think the process that we work with allows for a lot of tolerance. Like even if we are off by a few centimeters, the process still works. In case of the material, we do have a window which can be accommodated in the process. So what Lauren mentioned is this adaptive mix design. I think here having expertise on having a rapid decomposition of the material, in our case, because it's so variable, and then adapt the mix, works on the fly. So I don't know, in our case we can do it, but there are processes which are really material sensitive, and it's time critical, like things start curing much faster. I think maybe someone from those processes should be answering this question.
But we can also vary our velocity. So when you have a stiffer material with higher yield stress, you can shoot with a higher impact force, which enables still the bonding, but you do have a little bit of deformation. So then you end up with a profile of the wall that has bulging. Mm-hmm. So our process is very robust in that we can vary the parameters to respond to a mix design that's slightly off. And then with Kunal's tamping workflow, in theory, we could correct and still achieve a homogeneous section. Mm-hmm. But the sophistication on our side is maybe a little bit on the material, but more on the process side, whereas the sophistication on concrete 3D printing, because it's about, you know, really a very complex hydration process, is more complicated on the material side.
Mm-hmm. I had a question. I was just, I think your provocation about the next FABRICATE, and maybe the papers shouldn't be about novelty, but could also be about how getting closer to industry. I think it is a really relevant discussion that we need to have. And I wanted to point back to what Philip was saying in the former session, where you were asking, is it going to be rapid enough, and are we going to be fast enough for these very large challenges that are? I felt, yeah, we are. But I felt that the point is not one solution. The point is distribution. And what we're looking at here is such a beautiful array, and also over the 2 days, is such a broad array of different solutions. And as you're also saying, they are not in competition, they are in plurality. And it is this distribution of plural solution spaces that is really our only option out. So I was just also remembering that the session is on integrate, and I think when we were discussing this as a panel, we were very much thinking integrating building systems, and that's also what the debate is. But maybe it's also this integrate with industry. Mm-hmm. So what are the thresholds? How are these things brought together? And also what Anas was talking about before in the first session is really like, great guys, there's a lot of interesting solutions here, but there are real thresholds that you need to address. And I think there is something at stake in your project specifically, but of course also broadly speaking, which is about how do we then meet those thresholds. I think one of the things we have been very excited about in the editing of the whole volume is when things start becoming close to community and close to practice, not necessarily in a monolithic way, not in the same way, but in the multiple ways. So.
Do you guys want to respond to any of Netta's comments?
I fully agree. It's a very important point. We will not, I mean, there is currently a multitude of building methods. If one would always clearly be better, then that would have been the case for quite a while, right? So, but we see all those different building methods in different countries applied in different combination, and that makes a great deal of sense. And that will also be in the future the case. Not everything will be digitally fabricated, and that is also perfectly fine. So coming from that point, very important. I think what the challenge that, again, in this building industry that we face in the US is actually slightly easier on that end. I'll come to that. That when we want to educate the industry, we're talking about the bloody largest industry in this world. If you consider the 10 biggest contractors in Central Europe, and you convince all of them, your market share is going to be 2%. Right? The average contractor in Germany has 8 people working for him. So if you want to really convince all of these people, then there's a lot of integration work to be done. And how do we do that? How do we make it simple in adoption? And then we can really integrate all of them. And of course, the planning and the design plays a huge role in that. If it's not planned for digital fabrication, you've already lost. So there we have a big integration challenge, and again, in some countries of this world, there's actually big contractors that don't just do huge structures. So again, Central Europe, if you go to the big guys, they're just going to do bridges. And there it's going to be tough to get a new building system into a bridge. Hence, maybe you start with a single-family home because it's a lot easier on that end, at least on the permitting side and on the cost side, and then scale it up. But single-family homes in Central Europe are only built by small companies that are, again, lacking the R&D muscle power. In the US, that's slightly different. So maybe you pick and choose the country that you're doing it, and that makes it a little more easy. But yes, this integration will be key.
I wanted to pick up on the topic of community for just a moment, and maybe address your project specifically, Sasha, Leslie, and Fabian. Houston is an interesting city, and I mentioned the sort of stark contrast in terms of the siting of your project and the rest of the neighborhood. And yet you've had hundreds of people come and visit, both the media and locals, people curious about what you're doing. So I'm just curious if you could say a bit more about your experience in the making of this project and how it has impacted and touched the community in different ways.
Yeah, actually, I think that really start with finding the site. First, Houston is a city without, robust zoning, and therefore that's why it's such an interesting place. But there are many residential neighborhoods still have deeds restriction that the building needs to look a specific way. It needs to have a specific material, just like every other house. And then finding neighborhoods that actually doesn't have those deed restriction was actually the first step. And that actually allowed us to arrive in a very diverse community that it's full of both people who's been there for generations, but also immigrants, like new Houstonians in a way. So the community is very diverse. And when we, started constructing, there was so much interest, and the neighbors were actually all very excited. At first they were concerned because when they looked at our foundation, they thought we're building like a condo because it didn't look like a typical single-family house construction. And so I think the response has been kind of positive and embracing of something new and exciting that is happening in Houston. And so I think without that support, we would have a lot more challenges. Of course, there's the sort of people side, and then we are also looking at there are two types of housing, residential building that are prevalent. One is the single-family house, and the other are apartment buildings. There are two-story apartment buildings. And so actually on the other side of the site is an entire street of townhouses and condos that actually speaks to maybe a bit more of the sort of massing language that the project lends itself to. And I think kind of looking at both sides of those was an interesting process for the project.
I think we have time for one last question from the audience.
Thanks. I want to challenge a few of the approaches by referring back to the session this morning, where I think very convincing arguments were made that circularity is extremely important. In my opinion, it's actually the only strategy that in the long term will pay off. All other strategies push problems on the next generations. And so I would like to have maybe a reaction or particularly from the large-scale on-site kind of printing, locking in specific solutions, maybe jeopardizing potential future reuse or extending lifetime, mixing materials in inseparable ways so that it's doomed for landfill only at the end. So my point is more about these kind of approaches in a context that, again, in my opinion, but I'll say it very clearly, circularity is the only thing that matters.
I fully agree with you on that, by the way. It's just a matter of taking one step at a time. I mean, looking back a couple of years, our mixes from various material providers had a huge cement content, right? And that isn't good. And they had fibers in them and whatnot. And now we've moved towards conventional mixes with the cement content is comparable to conventional concrete, or not just comparable, it's in the same norm, right? Larger aggregate sizes, taking down the cement size. And certain parts of other projects that we have done, we've used blow-in insulation so that we can easily separate the pieces and make sure that they're recyclable, right? So you're perfectly correct. That doesn't mean that we can't take intermediate steps. If you try to learn how to ride a bike, so you try to learn how to figure out this problem of circularity, and you get on the bike the very first time, you're not going to be able to go over the Alps, right? The first time you're going to fall down a whole lot. And then you need to practice and practice and practice. So goal-wise, fully on board, that's where we got to go. We might have to accept that there will be intermediate steps.
Yeah, thank you, Philippe, for that question. It's a really important question to ask, and I think it's fair game. There's issues with spray foam insulation and circularity. We're aware of that. We looked at a variety of systems and chose this for this particular context right now, acknowledging or not being aware of some of the issues and problems. I think there are sort of smaller glimpses, especially in this project, where maybe there's a kind of flexibility built into the cores and the kind of infill in between that allows for a kind of reconceptualization of a concrete 3D printed house. But in the context of a kind of full circularity, 100 years out, there might be issues with this as well, which is also why we've been now looking increasingly at actually sort of precast printing on site, and so making concrete components that could be reutilized at a larger scale through a more circular framework. So I think that's why these conversations are really important. These types of forums are really important, and I think it's also really important to acknowledge that, you know, hopefully the future of housing construction is not all going to be 3D printed, right? This might be, we still have to hone in the particular use cases better for projects like this, or projects that utilize on-site 3D printing. But this is by no means a claim that this is the only way to build things, and this is also a public acknowledgement that it's really, really important to have a diverse range of building technologies, material systems to be working with.
Our project is, 100% motivated by being completely circular, but even in our case, using excavated materials or a circular byproduct material that's coming from a construction partner, it's not even necessarily 100% circular, because if you use any stabilizer, 1%, 2%, could be lime, could be cement. Obviously, if we use cement, we get much higher mechanical properties, which is advantageous. But as soon as you use more than half of 1%, you're already in the territory where when you crush it and then retry to use it and introduce it to your mix, you already compromise the mechanical properties in the second cycle. So for us to take circularity seriously, even if we look green, if we look circular, we actually have to crush the material, validate that we get find a nice blend that's maybe 20%, 80% of new excavated material versus old, and validate that we can get the same mechanical properties in the second, third, fourth cycle. So it's non-trivial even for us, and certainly I think concrete we should be asking, can this ever be circular?
So with that, we're unfortunately out of time, but I want to thank the audience and all of the delegates for your excellent questions, and please join me in congratulating our presenters on 4 just absolutely stellar, thought-provoking presentations.